charging downstairs. So at some point I might have to run down there and get it, but that'll be fine. So how's the studying going for everybody so far? How's this feel? Does it feel pretty good overall?
Yeah, pretty straightforward.
You know, it's kind of 3 different areas that correspond to the 3 chapters. Chapter 5 is just the eigenvalues and eigenvectors with no differential equations involved. And you just ask questions like, is this matrix defective or not defective? Can you build the invertible matrix S such that S inverse AS is equal to D, which is a diagonal matrix with the eigenvalues down the diagonal. And then there's a few theoretical type questions involving eigenvalues and eigenvectors. So the one that was on the quiz, that last problem on the quiz, definitely you want to know how to do that sort of problem. The other place where you can find some good practice on the theoretical problems with eigenvalues and eigenvectors is back in the homework, 5.6, number 36 through 38. Those are all really good problems. They were all part of your assignment a while back. But basically the test goes back to that stuff. So that's chapter 5. We did that right after spring break. So this test is covering everything since spring break, really. And then the middle part of this section is the higher order differential equations, linear differential equations. So you need to make sure you know the annihilator technique and the variation of parameters technique. You need to know that if you look at my sample test, you'll see that I'm probing you for more than just that. I also want you to know the general concept of building a general solution to a non-homogeneous in 3 steps. Find the complementary function, find one particular solution, and then add the 2 together. And then you have to know what it takes to get the complementary function. And that basically comes down to knowing the order of the differential equation. So if it's nth order, then you need n linearly independent solutions. Okay? And so the one on the sample test, I was actually very proud of that question. I basically gave you some of those solutions, and you didn't have to come up with them, but you had to verify that they were linearly independent by using Wronskian, and then you had to piece together the complementary function with the particular solution. So, so make sure you understand that little bit of theory as well. You guys have taken 2 tests with me already. You already kind of know that although most of the test is just going to be do the process, do the procedures, I do want people to have a big picture of what's going on here. So there's those 3 steps to solving those higher order differential equations. And then the last part is the vector differential equations. And for that, we have a different Wronskian, but we still have an n-dimensional solution space. We've only looked at homogeneous systems so far. The one last thing we have to talk about next week is going to be the non-homogeneous case, and I'll do that next week. For right now, it's all homogeneous, and we've looked at defective coefficient matrix, non-defective coefficient matrix. The 2 main things that people usually have the most trouble with are the complex numbers when those come up. You have to know how to sort of extract 2 real solutions from that complex expression that you write down. That involves doing that FOIL method. And then the other part of it is the defective matrices with the W1, 2, 3, 4, and 5, which we just covered last time. Okay? So those are kind of the things you need to know. That's basically it. You don't really have time to redo all the homework. If you're going to look at group works, I put a note on my website, but just so you know for sure, the group works that are most worth looking at are those 4 right there. Those are the ones that we've done since spring break. Although we didn't do 14 because they ran out of time last Wednesday, so actually I was going to do that today. So look at the group work, look at that sample test, and the review packet has a lot of problems in it too. So there's actually tons of stuff to look at. Does that make sense? Okay. My voice getting back to all you guys there in the peanut gallery so far? My dad's a doctor, so I called him up this morning and I said, I gotta do a review session today and I can't barely talk, what should I do? He said, just do a lot of writing and don't say very much. So I don't quite know how that's supposed to work, but we'll see. Let's start off by doing the problem that's on the group work 14, which I was going to have you guys do on Wednesday. Here's what we could do to rest my voice. I'll get more of you guys to give me the ideas. Okay. So before we get to the actual review session problems, let's look at group work 14. So here's problem number 1 from that group work. I'll write it down in case you don't have it. So consider x1 prime equals negative 6x1 plus x2, and x2 prime, well, let me say it this way, and x2 prime equals 6x1 minus 5x2. And part A is, what is the fundamental matrix? By the way, most of the time in the homework, when we were talking about questions like this, I would have just given it to you in this format. This is the way we usually see those linear systems written. But here I've thrown a little bit of a different look to the problem at you, just to make sure you still realize really this is more or less can be rewritten like this. Does everybody agree with that? You see, you can take these two equations, kind of lay them on top of each other, or put one of them above the other one, and then you see that really, really you just have x prime, right? And can somebody tell me, is there a capital A matrix that you see there? Yeah, just like that, right? So keep in mind that even if I write them like that, it's really just the same thing as this. And the point is that x is just the vector of x1, x2. Okay? Does that make sense? Okay. So this is the matrix capital A. Can somebody remind me, what is the fundamental matrix? Does anybody remember that term? I haven't emphasized it a lot, but I did mention it. I defined it in class. Does anybody know what it is?
The matrix made up by vectors x1 in the first column, x2 in the second column?
Right, it's the matrix where you actually put the basis solutions into the columns. So if I gave you two solutions to that system and I said are they linearly independent or not, what you would do is use the Wronskian. And the way you would build that matrix that you were going to take the Wronskian of is you would put the solutions into the columns. So the Wronskian is literally the determinant of this fundamental matrix. Right? So when it says what is the fundamental matrix, they're actually asking you to go through this whole solution process. Okay, so this is pretty fresh in our minds because we've done it recently, so let's do it kind of quickly. If I have a system like this, what's the first thing I want to do?
A minus lambda I.
Okay, so take A minus lambda I, so that would be negative 6 minus lambda, 1, 6, and minus 5 minus lambda. Remember guys, I'm going to give you the entire 2 hours to do this test. Please do not make silly mistakes, especially at the beginning of a problem like this. It's just going to be a disaster. You really have to get this lambdas correct. So I build that matrix, and then what do I do with that? Right, determinant of that. This one is just 2 by 2. So it's 2 by 2, it's going to be negative 6 minus lambda, negative 5 minus lambda, and then minus 6. Okay? And if you write that out as a quadratic, it's going to be what? plus 24, right? Lambda squared plus 11 lambda plus 24. Does that factor nicely?
Yeah.
Remember, it always factors, right? So you can always use the quadratic formula. If you're sitting there and you can't figure out how to factor it, don't freak out. Just use the quadratic formula. So in this case, it's going to factor how?
Lambda plus 3, lambda plus 8.
Good. So my eigenvalues are what?
-3, -8.
Okay, you know what I need to do? I need to give you a serious hint, which I'm not sure if I gave you, I cannot remember. But somebody here will remember for sure. As a way of checking that your lambdas are right, there is a little trick. Have I told you about this? That if you multiply the lambdas together, what you get?
No.
It's in the sample test. So I actually asked it as a test question last year in this class. But here is a nice thing to remember. The determinant of the original matrix, actually let's figure out what that is. That would be 30 minus 6, which is 24, is always the product of the lambdas. I never told you that?
Yeah.
It's kind of handy. This will not find all of your lambdas for you necessarily, but that is handy to know. Did I say it before? Okay, so maybe I did mention it. I can't remember. Maybe I forgot to tell it in one of the classes. I got people from both of my classes here. Anyway, so yeah, the product of the eigenvalues is the determinant. That's kind of handy to know. There's actually another formula. You guys are going to hate me, I didn't tell you this before. If you add up the lambdas, there's also a formula for that. The sum of the lambdas has to add up to the trace of the matrix, TR of A. I don't think I've gone over that with you. The trace of a matrix is simply the sum of the main diagonal. If you add up the main diagonal of a matrix, then that's called the trace. Sum. Does that help a little bit? Kind of nice to know. The reason one of the reasons I don't focus on it is because it's kind of hard to explain why that's true. But people are having enough trouble getting the lambdas right that I'm going to give you every tool I can to make sure you get them right. So these two numbers, they add up to -11. That is the trace of this matrix, the sum of the diagonal entries. Yeah?
It doesn't always work. It doesn't work with complex numbers, right?
It does.
It does?
It does work with complex numbers. The trouble with this is if your matrix is big, then you'll have lots of lambdas. And this equation, you only have two equations here and you have lots of unknown lambdas. So these two equations alone usually won't be enough to sort of figure out the lambdas for you. But they are a nice way to check your answers. So you get these two, the product is 24, the sum is -11. So you check the trace is -11, the determinant is 24. Just to make sure you did it right. Or sometimes you find all of the lambdas except one of them is giving you trouble. Well, you can sometimes use these two equations to figure out the missing lambda that you didn't find yet. Okay, I'm not going to ask you any questions on the exam that require this information because I didn't really emphasize it in class. But if you know the information and want to use it to check your work, more power to you. Right? I'm not going to stop you from doing that. Okay, so we have our two lambdas. The next step is to find what? Right, the null space corresponding to these two eigenvalues. So I've got to do the null space of... First thing I need to do is add 3 to the main diagonal of this matrix. So if I add 3, I'm going to get -3 and 1, and then I'm going to get 6 and -2. These rows have to be multiples. I mean, it's so funny. Somebody on the homework that I'm grading, I don't think there's anybody in here, but they had some matrix like this. They'd gotten the lambdas wrong, which is always the big problem. So somebody had gotten the lambdas wrong. They had some matrix that was like this, and they had some row crossed off, and I'm looking at it. Those are not multiples of each other. They're not crossing off a row. So check it. Make sure that these are actually multiples of each other. For a 2 by 2, that's another smoking gun if you did it right. If you're not getting multiples of each other, then you must have done something wrong. Now, can you tell me, without doing any real serious work, what would be a good vector here?
1, 3.
Yeah, 1, 3. Okay, great. And now let's do the other eigenvalue, which is -8. We're going to have the null space of, I have to add 8 to the main diagonal, and that's what I'm going to get right there. They are definitely multiples of each other. Can somebody give me a vector that I could use here? 1 and -2.
So how do you get the fast way you get the vector?
How do I get that so quickly? Well, the way I do it is I switch these two numbers
Just like that?
and then change the sign of one of them. Only works for like this little 2x2 situation. If you have a 3x3, like it was 2, 1, 1, then you actually have two free variables. You're actually going to get two vectors, not just one. And so you're not going to play this game. If you have to, you can always go back and do it the hard way, right? The hard way is write down the equation, set up free variables, and solve for the leading variables. And then bust out those free variables. Okay. So we've got eigenvalues, we've got eigenvectors. What's next?
Put those vectors into a matrix to get the fundamental matrix.
Let's do one step before we get
Get the
there.
Okay.
eigenspace for each eigenvalue.
The eigenspaces are just the spans of these two vectors, so we've pretty much got that. But what do we do to build our solutions to the system?
Oh,
That's the general solution, but how do I get a single solution here?
e to the
Say-
negative,
Right, let's call it x1,
e to the lambda.
right, e to the lambda t times v.
Yeah.
So it'll be like that. And then the second solution, e to the -8t times 1 -2. Okay? So now we're ready for what Curtis told us, how to build the fundamental matrix. Basically, this expression right here for x1 is a single column. This expression for x2 is a single column. So we can build those two columns, and we'll get a 2x2 fundamental matrix, which I called capital X, if you remember. And I think it's a little easier here to actually multiply the scalar into the vector. So this is going to be e to the -3t, and then 3 e to the -3t. The second column is e to the -8t, and -2 e to the -8t. There's your fundamental matrix. Okay? So if I ask you for the fundamental matrix, that's what I'm looking for. Yeah.
So whenever we just see the x without the vector thing on top of it, that's just the fundamental matrix?
Yeah, it's capital X.
Okay.
There's one way to really tell, but that's the notation we're using.
Okay.
Everybody good so far? Okay. Part B is to actually write down the general solution. So we did all the hard work in part A. So part B, we literally can just write down the answer. Does anybody know what it is?
x1 plus x2. Or c1 x1 plus c2 x2.
Right, C1 times X1 plus C2 times X2. You guys are welcome to refer to what you had written down earlier. You don't have to write it all out again. So you can just leave this as X1 as long as I can see X1 here. Or you can plug it in, so it's C1. Sometimes people like to look at it. And that's how it would look. Okay? That's the general solution. You guys with me? So far so good? All right, final question, part C. Is the origin of this system a source, a saddle, a sink, a spiral inward, a spiral outward, or a circle? It's a sink. It's an easy question because you just look at the lambdas, which I guess I erased, but the lambdas are both negative real. And you can see that as t goes to infinity here, doesn't matter what C1 and C2 are, as t goes to infinity, both of these terms are going to shrink to nothing. And so the position of the particle that's moving in this two-dimensional plane is going to be coming in towards the origin somehow, right? If I asked you to actually draw a phase portrait, I've never done that before, but I could ask you to do that. I don't know. We'll see whether I feel like I want to do that. Basically, the vector 1, 3 is that line, so everything's coming into the origin there. And this one is 1, negative 2, so that's right here. Everything along that line is coming into the origin, and then every other direction is also spiking into the origin, so that's why it's a sink. The trouble with asking you to draw one of those on the test is, how do you know how many lines to draw? What's a sufficient number? More likely thing would be me to give you like a multiple choice or something. Draw several of these and say circle which one would be the right phase portrait for the system. And then you'd be looking for the one where all the lines were going into the center. I might have other pictures that were spiraling or saddles or whatever. Okay. So I've never done that, but that's the kind of thing I like to do. Like I like to ask 1 or 2 questions that really test if you understand, if you can put the pieces together, even if you haven't quite done it in the past. So we'll see. I haven't written a test yet, so we good on that? Yeah, Curtis?
Is there any, so like originally they gave us x1 prime and x2 prime.
Yeah.
Is there any way to like check our answer with those?
All you could do, you could take your x1, take the derivative of it, put it right here, put negative 6 times x1 there, put x2 there, add it together, and just check the left side and the right side.
Okay.
That sort of thing should be, that would be a great thing to do. I'd be upset if somebody walks out of the test 30 minutes early and screwed it up and didn't take the time to check. But doing those kinds of checks should probably be done at the end.
Yeah, definitely.
Yeah. Did you hand up?
Yeah.
Go ahead.
How do you know again what if you have a sink or a source? Like what do you look at?
You look at the lambdas.
Okay.
If both lambdas are negative, then it's a sink. So in this case, I erased the lambdas already, but they were negative 3 and negative 8. So they're both negative, so it's a sink. If they were both positive, then we would have a source. And if one was positive and one was negative, then we would have a saddle. Yeah.
Thank you.
Make sense? Okay. Anything else about that? All right. There's a second problem on this report. Let me ask you about it real quick. It's going back to some of the older material, so should be okay. My voice still holding on.
So the circle.
I'm not going to talk much tonight.
The circle and the spiral has to do with it not being
Complex numbers. Yeah, complex numbers, exactly. Okay, so here's number 2a. I'm going to give you a differential equation. Y triple prime plus 3y double prime plus 3y prime plus y equals 2e to the negative x plus 3e to the 2x. Okay. And then the question is, discuss what technique you would use to solve that differential equation. So before we actually do anything, we want to talk about how we would do it. And that often is something that I care a lot about. It doesn't take very long to answer this question. Just what technique would you use? Part of what you have to do here, and we're going to play this game on Wednesday next week in an even bigger scope, which is you have to figure out where does this problem fit in the 7 chapters of this book that we have covered. One of the ways to, so there are some natural questions to ask. One question to ask yourself when you see a differential equations problem is it one differential equation or is it several? If it's several, then we're talking about a system. And if we're talking about a system, then we're talking about chapter 7, the stuff that we're just learning now. If it's only one differential, so that would be like the first problem. There were two differential equations, 2 counts as several, right? Anything more than one differential equation is a system of several differential equations. So that means you're using the material in chapter 7. Is this several differential equations?
No.
No, it's a single differential equation. It's one differential equation. Another important question to ask ourselves about the differential equation is, what is its order? If it's first order, well, we studied first order differential equations in chapter 1. That's not on this test, so you're not going to see first order differential equations on this test, but you will on the final, right? So you're going to need to be able to recognize those. So you look at the order and say, okay, it's a third order. So it's a single third order differential equation. So which chapter of the book is this problem coming from? 6. Exactly. And as soon as you know that, you should know that there's 2 possible ways of solving a third order differential equation. What are they? Annihilators and variation of parameters. So let's talk about it. Which of those would you use here? Annihilators. Why?
Because we don't do third order, what is it, the variation?
Right, variation of parameters I only showed you how to do for second order differential equations. So this must be a problem about annihilators, in addition to the fact that we do know how to annihilate the right hand side. Because these are very familiar functions, right? Okay, so we're going to use the annihilator method. So what's the first step?
R, get the complementary.
Okay, and how are we going to do that?
R to the third plus 3r squared plus 3r plus 1.
Equals 0.
Great, okay. Now, you're going to have to trust me that I'm going to give you a characteristic polynomial that you can factor. Or I'll factor it for you already. I expect everybody to be able to do quadratics, for sure, because you have the quadratic formula to factorize that. So this one's not quadratic, but does anybody recognize it? Yeah, it's actually r plus 1 cubed. If you sort of triple FOIL that out, you'll get exactly the thing in front of it. And so the roots are -1, -1, and -1. Now, I already gave you one little sort of tip here about like a nice trick to do stuff. Let me give you another trick. So you'll be happy that you came to the review, even though I can barely talk. The roots of the auxiliary equation, if they are rational or whole numbers, which they almost always have been, those roots, whatever they are, have to divide the constant term. So you're not fumbling around in the dark looking for the roots of this polynomial. The only choices are things that divide the constant term. That's actually a theorem from higher level math. 300 level math classes will talk to you about why that's true. The point is, the only candidates for the roots here are +1 and -1. But you can clearly see that +1 is not a root, because if you plug +1 into this equation, you're going to get a positive number plus a positive number plus a positive number plus a positive number, which will not equal 0. So the only possibility is that -1 is the only root that you have. In which case, you have to have it 3 times. So, does that kind of make... So, what I'm saying is, let's say you didn't figure this out. That this thing happens to factor out real nice like that. Even if you didn't figure that out, if you remember the trick that I just told you, that the only candidates for roots, we're not saying they are roots, but the only candidates for roots are numbers that divide ±1. At least the only rational candidates. If pi is a root, some irrational number like that, well then I can't help you.